All right, welcome back to the deep dive, everyone. Today we're tackling a topic that's, well, it's about as big as it gets in the universe.
Yeah, I mean, literally, we're talking about the universe itself.
Exactly. Specifically, we're diving into this thing called the Hubble tension.
Ooh, Hubble tension. That sounds like, I don't know, like a cosmic tug of war or something.
Kind of, yeah. So the Hubble constant, that's like the speed limit of the universe, right?
Yeah.
How fast everything's moving apart. And well, it turns out we're getting different readings depending on how we measure it.
Wait, so like different speed limits for different parts of the universe? I'm already lost.
Okay,
Yeah.
okay, good point. Maybe speed limit wasn't the best analogy. It's more like we're using different tools to measure the same speed, and they're giving us different answers.
Oh, okay, that makes more sense. So like two different radar guns clocking a car at different speeds.
Exactly.
Hmm.
And it's not just a small difference either, which would be, understandable with any measurement. This is a pretty significant gap, and it has cosmologists scratching their heads.
So walk me through this. How are we actually measuring this Hubble constant?
Well, there are two main methods. The first one is looking at galaxies that are relatively nearby and seeing how fast they're moving away from us.
So like a cosmic radar gun.
Right,
Oh,
basically. And when we use this method, we get a Hubble constant of about 74 kilometers per second per megaparsec.
mega what?
Right, sorry, a megaparsec. It's a unit of distance, and it's a big one. About 3.26 million light years. So for every megaparsec further away a galaxy is, it seems to be zipping away from us 74 kilometers per second faster.
Gotcha. So galaxies are basically playing a cosmic game of keep away, and the further away they are, the faster they run.
Aha, yeah, something like that. Now, the other way we measure the Hubble constant is by looking at the cosmic microwave background. It's like the leftover radiation for the Big Bang, the very beginning of the universe.
So it's like a baby picture of the universe. Cool.
Exactly. And when we study this cosmic baby picture, we get a Hubble constant of about 68 kilometers per second per megaparsec. So slower than the radar gun method, right?
Yeah. So the universe was expanding slower in its early days than it is now.
That's what it seems like. And that difference, that tension, is what we call the Hubble tension. It's like the universe hit a growth spurt that we didn't account for.
This is fascinating. It sounds like this Hubble tension could really shake up our understanding of the universe.
It definitely could. One of the most exciting possibilities is that it's a sign of new physics, something beyond our current understanding.
New physics, huh? Like what?
Well, there's this idea that quantum gravity could be playing a role. It's kind of like where the laws of the very big gravity meet the laws of the very small quantum mechanics.
Okay, so two very different sets of rules trying to play nice together. Sounds complicated.
It is, very much so. But some scientists think that quantum gravity effects in the early universe could have messed with the expansion rate in ways we haven't figured out yet.
I read that article in Popular Mechanics, the one you mentioned before the show. Hubble tension may be the result of new, unknown physics. It talked about something called a hybrid inflationary model or something.
Yeah, that's the one. It's pretty deep stuff, but the gist is that this model tries to use quantum gravity to explain the tension. It suggests that during the very early universe, when everything was incredibly hot and dense, quantum gravity could have affected how the universe inflated. That period of super rapid expansion right after the Big Bang.
So basically, are we saying there might be forces at play in the universe that we don't even know about yet?
That's the mind-blowing possibility. It's like
Yeah.
we have this model of the universe, and it works really well for most things, but then this Hubble tension pops up, and it's like, wait a minute, there might be a whole other chapter to this story that we haven't even begun to write.
So this Hubble tension, it's not just about getting the numbers right. It could mean there's a whole new set of rules governing the universe that we need to discover.
Exactly. And that's what makes this so exciting. It could be our first glimpse into a completely new understanding of the cosmos.
I'm officially intrigued. What else could be causing this tension?
Well, some scientists think the answer might be even more radical. The universe could be much older than we think,
Older. How much older are we talking?
like twice as old. The commonly accepted age is about 13.7 billion years. But some researchers are suggesting it could be closer to 27 billion years.
Whoa, that's a big difference. I mean, 13 billion years is already mind-bogglingly huge, but double that. How could we have gotten it so wrong?
It all comes down to how we measure distances and the expansion of the universe. There's this idea called the tired light theory, which suggests that light might actually lose energy as it travels across vast cosmic distances.
So, like, light gets tired on its journey. I've never heard of that before.
Yeah, it's a bit of a fringe theory, but it's been around for a while.
Hmm.
The idea is that this energy loss could explain why distant objects appear to be moving away from us faster than they actually are, which would mean we've underestimated the age of the universe.
Okay, so instead of the universe expanding faster, maybe light is just slowing down over time.
That's the basic idea. It's controversial, for sure, and most scientists don't buy it. But hey, it's always good to consider different possibilities, right?
Definitely. I mean, who knows? Maybe this Hubble tension will lead us to a completely new understanding of light itself. But before we go too far down the rabbit hole, shouldn't we consider if maybe we just messed up the measurements? Like maybe our telescopes aren't accurate enough or something.
You're absolutely right. We can't get carried away with exotic new physics without first making sure our tools are up to snuff. And that's where the James Webb Space Telescope comes in.
Ah, yes, the James Webb, that amazing new telescope that's been sending back those incredible images. What's it telling us about the Hubble tension?
Well, early data from the James Webb actually seems to support the measurements we get from looking at nearby galaxies. So it's making the tension even more pronounced, really.
Wow, so even with our most advanced technology, this tension is still there, staring us in the face.
Yep. It's like the universe is giving us this cosmic riddle, and we're just starting to piece together the clues.
And it sounds like we've got some pretty big pieces to figure out. New physics, a much older universe. Where do we even begin?
That's what we're here to explore. We're going to dive into the potential implications of this Hubble tension for the evolution of galaxies to the mysteries of dark matter and dark energy.
All right, I'm ready for the deep dive. Let's see what other secrets this Hubble tension holds.
Okay, so we've talked about what the Hubble tension is, but what does it all mean? Like, why should we even care about this cosmic discrepancy?
That's the big question, right? I mean, it's not like this tension is going to affect our daily lives, make our coffee taste bad or anything.
Right, but it could change how we understand well, everything.
Exactly. It's like, imagine you thought you knew how a car engine worked. You knew all the parts, how they fit together, the whole thing.
And then one day you pop the hood, and there's this extra part just sitting there that you've never seen before.
Right. And it's not just some random bolt or something. It's connected to everything else. Suddenly you realize your understanding of the engine was incomplete. Okay, yeah, I get it. So the Hubble tension is like that extra part in the engine of the universe. It's telling us there's something we're missing, something fundamental.
Precisely. And figuring out what that something is could completely revolutionize our understanding of the universe, its history, its evolution, maybe even its ultimate fate.
All right, I'm on board. So let's break it down. What are some of the big implications of this Hubble tension?
Well, if it turns out that new physics is the culprit, as that Popular Mechanics article suggests, it would mean rewriting the textbooks on cosmology. Our current models of the early universe might be missing some crucial ingredients.
And that would have ripple effects throughout all of cosmology, wouldn't it? Like how galaxies form, the distribution of matter, all that stuff.
Absolutely. This is the thing about it. The universe starts with the Big Bang, right? And then it goes through this period of rapid expansion called inflation.
Okay, yeah.
Well, if quantum gravity was messing with the expansion rate back then, it could have changed how matter clumped together to form the first stars and galaxies.
So the very structure of the universe we see today, those giant clusters of galaxies and cosmic filaments, could have been shaped by forces we don't even understand yet.
Exactly. And that's just scratching the surface. It could also have implications for dark matter and dark energy.
Yeah, those mysterious components that make up like 95% of the universe. We know they're there, but we have no idea what they are.
Right. It's like knowing the characters are on stage, but not knowing their lines or motivations. And maybe this Hubble tension is a clue to what their roles really are.
So new physics could explain dark matter and dark energy. How does that work?
Well, it's possible that there are particles or forces associated with dark matter and dark energy that we haven't discovered yet.
Okay.
And maybe those particles or forces were interacting in the early universe in a way that affected the expansion rate, kind of like a hidden hand guiding the evolution of the cosmos.
Wow, that's a pretty wild thought. But even wilder is this idea that the universe could be twice as old as we think. I mean, is that even possible?
It's definitely a radical idea. But remember that tired light theory we talked about? If light does lose energy as it travels, it would mean that distant objects appear to be farther away and therefore older than they actually are.
Ah, right. So we might have misjudged the distances to those faraway galaxies, and that's throwing off our calculations of the age of the universe.
That's the thinking. Of course, there's a lot of debate about whether tired light is a real thing, Most scientists are pretty skeptical.
I can see why. I mean, it would mean that our understanding of light, which is like one of the cornerstones of physics, is wrong.
True. But even if the tired light theory turns out to be a dead end, it highlights just how much we still don't know about the universe.
It's like every time we think we've got a handle on things, the universe throws us a curveball.
Exactly. And it reminds us that we always need to be questioning our assumptions, looking for new evidence, and being open to new possibilities.
So, okay, we've got new physics, a super old universe. But before we get too carried away with those ideas, is it possible that the Hubble tension is simply due to some kind of error in our measurements?
That's always a possibility, of course. Measuring the expansion rate of the universe is incredibly complex. We're talking about observing objects that are billions of light years away, and there's a lot of room for error.
Yeah, I can imagine. It's like trying to measure the width of a human hair from across a football field.
More like across the entire state.
Yeah.
And then you have to factor in things like the motion of galaxies within their clusters, the gravitational pull of intervening matter, and even the expansion of space itself.
So even tiny uncertainties in our measurements could add up to a big discrepancy in the Hubble constant.
Exactly. And that's why scientists are constantly working to refine their techniques, improve their instruments, and cross-check their data.
But you said earlier that the James Webb Space Telescope, our most advanced observatory, is actually making the tension more pronounced.
Yeah, that's the crazy part. Its observations are so precise that they're ruling out some of the potential sources of error, which means the tension is likely not just a measurement fluke.
Wow. So even with our best technology, we're still faced with this fundamental mystery.
It really is a cosmic puzzle. But that's what makes it so fascinating. It's a challenge to our understanding, a call to explore new ideas, and a reminder of just how much we still have to learn about the universe.
I'm starting to see why you're so excited about this Hubble tension. It's not just about numbers and equations, it's about pushing the boundaries of what we know.
Exactly. And who knows what incredible discoveries might lie on the other side of this mystery. It's a journey of exploration, and we're just getting started. It's amazing to think how far we've come in our understanding of the universe. I mean, a few centuries ago, people thought Earth was the center of it all.
Right. It's wild how our perspective has shifted. And now, this Hubble tension might be pushing us toward another major change in how we see the cosmos.
Exactly. And, speaking of shaking things up, we talked earlier about the tired light theory. It's a pretty out there idea, but I'm curious to hear your thoughts on it.
Yeah, the tired light theory, huh? It's definitely intriguing, the idea that light could lose energy as it travels these incredible distances. But it does go against some pretty fundamental principles of physics.
For sure. And the vast majority of scientists don't actually support it. The evidence really points to redshift being caused by the expansion of space itself.
Right. But, even if it's not the right answer, exploring these alternative theories can still be valuable.
Totally agree. It forces us to really examine our assumptions and look at things from different angles. It's all part of the scientific process, right?
Absolutely. Testing ideas, challenging theories, constantly refining our understanding, that's how we make progress.
Exactly. So even if tired light isn't the solution to the Hubble tension, it's a good reminder that there's still a lot we don't know, and that we should always be open to new possibilities.
Well said. That spirit of curiosity and open-mindedness is really what drives scientific discovery.
It is. And it's led to some pretty incredible breakthroughs already, wouldn't you say?
Oh, absolutely. The things we've learned about the universe in just the past century are
It
mind-blowing.
makes you wonder what other mysteries are out there waiting to be uncovered.
So many, I'm sure. And with the amazing tools we're developing, like the James Webb, I think we're on the cusp of some truly remarkable discoveries.
Couldn't agree more. It's an exciting time to be involved in cosmology, that's for sure.
It is. The Hubble tension, even though it's a puzzle, is really pushing us to expand our knowledge and dive deeper into the workings of the universe.
And in a way, isn't that the whole point? To explore, to question, to learn, to appreciate the sheer wonder of this cosmos we're a part of.
Couldn't have said it better myself. The pursuit of knowledge is a journey, and it's a pretty amazing one to be on.
Well said. And on that note, I think we've reached the end of our deep dive into the Hubble tension. It's been a fascinating journey.
It really has. Thanks for guiding us through this complex topic. I know I learned a lot.
The pleasure was all mine. And to our listeners, thanks for joining us on this cosmic exploration.
Remember, the universe is full of mysteries just waiting to be solved, so keep looking up at the stars, keep asking questions, and never stop exploring.
Because who knows? Maybe one of you listening will be the one to crack the code of the Hubble tension and lead us to the next great leap in our understanding of the universe.
Until next time, Keep those minds expanding and those imaginations soaring.
And that's a wrap for the deep dive. We'll catch you next time for another adventure into the mysteries of the universe. See you then.